and thank you for joining in today. My name is Shelly DeGrate, and I am the Industry Strategy Director here at Grace Technologies. At the end of this discussion, I'll be addressing any questions you may have, so please feel free to type them in the chat bar when you, as they come to you, and we'll address them here at the end. 33 years ago, I witnessed a man get his thumb blown off of his hand, reaching down into an energized cabinet for a tool that he had dropped. 23 years ago, I experienced a phase-to-ground flash in my face. It burned my hair, my eyebrows, my eyelashes, and I thought it took my eyesight. I was not wearing safety glasses. I was not wearing a hard hat, and I was at the top of an aluminum ladder. In the recent past, it was common for plant electricians to open an energized cabinet for inspection and testing using everyday clothes and equipment. However, nowadays, if you are even allowed to open the door, you have to do it with the appropriately rated PPE. Thankfully, over the years, we've all experienced the evolution of better electrical safety practices, standards, and products. Improved personnel safety is the predominant reason why facilities are embracing these new technologies to execute these hazardous tasks without sacrificing the end results. Today, we'll be discussing a technology that's near and dear to my heart because it is one of those safety-oriented products that could save a life one day, and maybe it already has. Temperature measurement has typically been a good way to understand the condition of different things, whether it's bearings in a motor or your sick child, for example. In electrical equipment, temperature escalation is a really good predictor of potential failures, but the traditional method of thermographic scanning to gather information only is capturing a snapshot of the actual operating temperature of the equipment at a specific moment in time, and therefore does not provide the full life cycle story. So before we dive in, we have a couple of survey questions for you guys to answer. So Nick will pull those up for us. So we're often asked, what are the causes of temperature escalation? Why would I find a hot spot in my equipment? Well, the primary reason and why we thermal scan to begin with is for loose connections. But also there are other reasons why you might have this temperature escalation, and that would be varying loads, mechanical stresses, aging equipment, unmaintained equipment, or high harmonics or distortions. Let's face it, process downtime is costly, whether it's planned or unplanned. But when it's unplanned, and we're having to be reactive due to an electrical failure, it can result in several days of lost production. When you add the lost production with the equipment repairs or replacements, it could be tens of millions of dollars. So as the market becomes more competitive, the corporate focus is typically on a reduction in cost. So keeping the process units down for extended period of times are just no longer accepted. Therefore, the addition of products like a continuous thermal monitoring product could help the facility confidently extend the equipment's maintenance cycle and increase the process uptime. Thermal scans through windows do provide a partial solution to the problem by allowing the camera to capture thermal data within energized equipment. However, complete line of sight to all the critical locations can't always be achieved because there's often cables or safety barriers that are obstructing the view of these connections. So installing a thermal monitoring or continuous monitoring solution will not only capture the thermal data on energized equipment, but also reach those critical points well beyond what would be visible through a window. Maintenance cost savings can be recognized by eliminating the thermal scan activity, which would allow more focus perhaps on other tasks during a turnaround project. That's why many facilities are deploying a full continuous thermal monitoring solution, not only to save maintenance dollars and gain the relief of scarce human resources, but also to gain the insight of their thermal baseline of each critical asset on site throughout the course of the year, especially during the peak loading times. Grace's solution for continuous thermal monitoring is called the HSM, the Hot Spot Monitor. It has been in the market since 2010, and it has a wide breadth of industry applications unmatched in the market today. We're now going to play a whiteboard to illustrate further the HSM's fit in the market and product features.
In an effort to prevent expensive shutdowns and unplanned maintenance downtimes, facilities across the globe today rely on a variety of preventive maintenance methods. Many studies indicate that temperature rise, otherwise known as hotspots, is a major cause for these failures. These abnormalities are often caused by loose connections as a result of vibrations, unbalanced loads, overloaded conditions, and a wide range of other issues often found in conductive environments. Most industries use either routine physical inspections or thermography programs to detect temperature abnormalities. Physical inspections require the user to open the electrical enclosure, barriers, and other insulating materials in order to inspect the connections. Since most facilities prohibit their personnel from this type of high-risk access, the data obtained is often inaccurate or unobtainable. Additional risk of failure exists when the equipment is not put back in the original condition after inspections. To overcome these shortfalls and to measure the temperature of the live conductors, some facilities use infrared cameras and windows. With this method, an IR camera is directed at a live conductor either directly or through an IR window to measure the rise in temperature. In some cases, the IR camera or the window visibility is restricted by the connection location and field of view of the IR window. To help you address these concerns effectively, we'd like to introduce our new GraceSense Hot Spot Monitor, or HSM, a continuous real-time temperature monitoring device intended for locations that are difficult and hazardous to access. This device not only measures the temperature at any given point in time, but also proactively monitors and enables the user to predict the failure before a potential shutdown. The HSM utilizes patented fiber optic technology, providing constant temperature data available in 9 or 18 independent sources. The fiber probes can be mounted onto electrical bus bars, bus ducts, transformers, or any other source of heat. The Hotspot Monitor provides a unique combination of patented fiber technology and advanced algorithms that convert the change in light intensity to temperature. The patented fiber probes securely connect to a ring-style connector that conveniently mounts to the source of heat, while the other end connects to the HSM module. Sources of heat may include inaccessible equipment and blind spots to IR scanning. The most obvious benefits of the HSM over IR thermography come from the continuous real-time monitoring feature. In addition, the successfully proven measurement accuracy of the probes is not subject to calibration errors, as can be the case with IR scans. The Hotspot Monitor comes with 16 megabytes of built-in memory for data storage. By connecting the GraceSense HSM module via Modbus TCP/IP or Ethernet IP and accessing the web utility tool, users can configure the temperature thresholds, time intervals, and relay outputs. This tool further enables access to the real-time data logs and downloads the stored data for analysis and trending, connecting directly to the device or safely through closed doors using a GracePort Ethernet connector interface. GraceSense Hot Spot Monitor is a reliable and affordable solution for use in environments with low, medium, or high voltage systems. The HSM is available in 2 versions, either a 9-point module with a built-in LCD display or an 18-point module. The unit comes fully kitted with fiber probes, ring-style connectors, and an installation kit. Optional accessories include a Modbus current sensor, high-temperature probes, ambient measurement attachment, custom connectors, and fiber lengths of various sizes. Continuous real-time monitoring, our answer to your most demanding and critical applications where guesswork and downtime is not an option. Find faults before they find you.
So today we're going to talk about Grace's solution for continuous thermal monitoring, and it's called the Hot Spot Monitor, HSM. It consists of a monitor itself, and the fiber. This is a direct connect method by which to measure temperature at bolted locations throughout the equipment. So what we do is we pulse an LED light down this polymer fiber, and it reflects off this probe tip. What we watch and what's calculated in here are the sophisticated algorithms in here are actually calculating the temperature by watching the light wave attenuation over time. So the benefit to that is actually the fact that everything is cured inside this probe tip, and it's not necessary to ever have to calibrate it or do any kind of adjustments to it once it's installed. So for OEMs, they can boot over it, we can insulate on top of it, and you're still going to get a really good reading from that location. So the module itself comes in either 9 or 18 points. The 9 has an LCD display screen, so you can see the temperature and you can scroll through, all the different values and settings inside of it. It has a Ethernet cable, so either Modbus, TCP, RTU, or Ethernet IP as a protocol to go to a power management system or an existing a DCS, for example. And also it has an internal relay. This relay will close upon the temperature rise to the lowest level threshold that is set inside the product. The factory defaults are 90 and 105. So if a temperature, any one of these points temperature escalate to 90 degrees, it'll automatically close that relay and notify personnel either via a PLC, maybe even it goes through a protective relay, for example, a horn or some other method by which to get the alarm notification to the appropriate personnel. Inside the module itself is an internal web page. And inside that internal web page that's just pinged via an IP address is where you would do all the setup for if you want to measure in temperature in Fahrenheit or Celsius, change your alarm set points. There's 2 levels of threshold, so you could say one section is for a more critical load, so you'll want perhaps a notification on a lower temperature, or on the second set is maybe loads that maybe aren't as critical, and you can raise those or adjust those as needed. But the most important thing is to make sure that the alarm gets to the appropriate personnel and action takes place when necessary. The HSM probes come in 2 lengths, either 10 meters or 15 meters. We typically choose to provide in the standard kit anyway is a 10-meter length of fiber, and that typically gets anywhere within your electrical equipment that's needed. We kit it in that length because OEMs, for example, that are manufacturing switchgear or motor control centers or whatnot, 10 meters is plenty to get anywhere you need to go. Typically in field applications, since sometimes it's unknown, the 15 meter is the better one to get. They're all calibrated to the full length, so it doesn't matter if you trim it or not. And speaking of trimming, this is part of the kit. It's just a plastic encased razor blade, and you can just see that you use this to trim the end and make a clean cut and put it in. So another great feature about the fiber, the polymer fiber, is the fact that you don't have to have any special skill sets, tools, polishing equipment, or anything like that in order to get a good clean cut on this plastic fiber. The fact that it's non-conductive allows you to take it in any electrical environment without the risk of interference into control wiring or power wiring. It is it's effectively invisible inside these inside the conductive environment, electrical environments. The attachment of the fiber to a bolted location, what we call a fixture, is really nothing special. It's a ring lug, and the only difference is that the end of it needs to be a 6-gauge opening, 6-gauge wire opening, because that's the size of the probe. There's a piercing set screw inside this probe tip that actually secures it nice and tight into the lug itself. But there's nothing special about the lug. Again, we use tin-plated copper, but there's nothing special about it. We just want it to fit, snugly, fit snug so that the heat will transfer to the probe itself. There are other accessories associated with this product. One being the high temperature probe. The high temperature probe is about 11-inch segment of a fiber like this one, but it has extra insulation on top of it. So it allows the fiber, whereas the normal fiber is rated for 120C, the high temperature probe is rated for 160C. So what that does is allow you to get the plastic fiber further away from the heat source. So of course, then we don't want it to melt. If a delta T calculation is desired, we do have a solution to measure ambient. So there's two types of ambient connectors, if you will. One is a curved ambient holder for inside the equipment, and one is a standoff for perhaps on the profile of the equipment, stand off the profile of the equipment. So you know what's going on inside the equipment, it's what's going on outside of the equipment. We also have another accessory called the Modbus current sensor, and what that does is it behaves like a split core CT, but it attaches to the secondary of a primary CT, and you would do your full scale amp notification inside the web page of the unit itself. But what it does is it allows for the correlation between current and temperature. So the Modbus current sensor would be calculating current, and the temperature would be measuring temperature, and those two values would actually be logged inside the unit itself together. So when you download the data and you extract it and you put it down on your laptop, then you could easily see a trend on what the current is doing in relationship to the temperature. So let's talk applications. Obviously, there are a lot of different pieces of equipment that are carrying current. And as we know, increasing current increases the temperature. So what we want to talk about is where the most important points are within different pieces of electrical equipment to make it a viable point to monitor. So I always start out by asking, what do you currently thermal scan? There are many insurance companies that require an annual thermal scan. Some industries that are self-insured, they maybe do thermal scans every 3 years. However, with the continuous thermal monitoring solution, you will get it again continuously. So you'll know on a regular basis what's happening deep inside your asset. So for medium voltage switchgear, for example, we have determined that there are several points by which we consider a potential failure point. And that would be in the field terminations, right? The cable terminations where you're already thermal scanning if you have that program going. So cable terminations, your line and loads side of your breaker, even if it's on the run back, it's okay. A PT rollout compartments, maybe your main bus entrance, maybe or your main breaker entrance and your main bus and the equipment. Transformers, for example, on the secondary side of your transformers. Medium voltage, switch MCC, perhaps on the T leads and main bus. Contactors, any moving components, any moving locations. We always like to get medium voltage drives is a completely different story. There are, hundreds and hundreds of voltage connections in medium voltage drives. One way we like to really look at it is those points by which have either hidden or they have the potential to get hot. So we do look at those. There's probably upwards of 36 points per medium voltage drives, depending on who manufactures it. That would be a very interesting point to obtain. We call it a point of interest too. In low voltage equipment and switchgear, for example, It is often hard to get a thermal scan on a riser of cable connections from low voltage switchgear. So getting those cable terminations in switchgear would eliminate the need to try to bob and weave behind the different connection points going to the different low voltage breakers. So those cable chimneys are definitely in the way. So getting those monitored would be great. Low voltage motor control, again, this can route with power cables and comm cables. So anywhere within the low voltage equipment could easily be monitored as well. In recent years, I've been asked questions like, where do I install them? Do I install them on all bolted connections? And in this day and age, really, it's anywhere that has a human interaction, human contact to it, or inaccessible, or locations that are kind of be hidden, either from real estate constraints where your equipment is up against a wall, or in situations where that human contact is going to be there. We want to try to really take those points that might have some extra vibration issues, some points that, again, are covered with barriers or have that cable terminations in locations like this. I've also recently have been much more involved in medium voltage drive applications. These drive applications out in the sun in summer, it gets in these extreme heat locations. It's very important to monitor locations like that, so as to catch that impending rise in temperature. So some typical applications in medium voltage switchgear, we see line and load on the breaker stabs or on the run backs of the breaker. We see them on PT rollouts. We see them located in the main bus chamber. We see them obviously in the field terminations, perhaps shipping splits as well. Those are all, some of those are locations that, have that human contact to it. But also in MCCs, the field terminations, the contactors, in switchgear, again, really tight locations, trying to get there. There's no size constraint on the lug or what we call fixture on this. It just has to have a 6-gauge wire opening because that's the size of the probe. But you can use rings, you can use 1/4-inch rings, 3/8 rings, 1/2-inch rings, or heck, I've seen people use thermal tape to tape it in place. There's so many different solutions. So let's talk about the embedded web page for a minute. We chose not to integrate or to develop a software for this product because we felt like it was the best product to be integrated into one's own system, power management, DCS, or what have you. So what we did is we embedded a web page inside the module itself. That way, all the setup could be done there. The data extraction could be done there. And most importantly, the setup of your alarms can be done there. So there's 2 sets of alarms, a primary and a secondary set of alarm. So a primary would be one where perhaps you would lower the alarm level as opposed to maybe a load it's not as critical, and you would keep that one perhaps at 90 and 105, which are the default values. But logging the temperature and doing the setup in here is important, but not as important as making sure that the alarms are set up to warn you or warn the system that the temperature is rising. So we always recommend marrying the temperature and a current with that circuit on the same trend screen. So you can visually see that escalation together, because we would expect a linear relationship between temperature and current. So if you see a temperature escalating with stable current, that would be a red flag that would need to be checked out. But going back to the HSM embedded web page, the things that could take place inside the setup are, for example, enabling that relay normally open relay that we talked about. that can be enabled inside the web page as well. So if you have a critical load, you could actually check the checkbox to close that on that particular point, that particular channel coming in, and maybe not others that might not be as critical. So setting the alarms is crucial, but also getting the notification that you have an alarm and having that visibility is paramount to the continuous temperature monitoring process and product in general. I also want to talk to you about the concept called dark fiber. This is a situation where a shutdown happens either on schedule or not on schedule, and you have the opportunity to install the fiber because the equipment is de-energized. We highly encourage take this opportunity to install the fiber, get it routed up into your low voltage compartment, and that way, when you do have to energize, the system is ready to go, and we don't have to worry about maybe taking the time to install the electronics at this time. So we typically have fiber on hand all the time. So to call us up and say we need it because we have a shutdown, it's only going to be down for a few days, would be a great opportunity to also get this product in there. Then we can come back and install the electronics and do the setup and all that at a later date. But it's not as critical to get the electronics in as it is to get the probes attached inside the high voltage areas. And finally, I do want to talk about the fact that the IEEE PCIC committee has approved a PAR, which is a project for us to develop a guide for continuous thermal monitoring for switchgear and motor control centers below 52 kV. So hopefully this has piqued an interest to you, and you can read more about the general requirements of the application, considerations, system requirements, and then you can develop your own thoughts of where and how you want to monitor your critical assets. Has it been used in a high vibration environment? To my knowledge, it has been used in mining equipment. I don't know the exact application, but if there are other bolted connections and you have a torquing procedure, I don't see why this would not be able to work there. Do we offer a three-phase current monitor? Is your current separate Ethernet connection? No, it actually goes into the RTU or the DB9 connector. So it would just communicate via Modbus RTU. So you can put one Modbus current sensor on each phase, and then that would go into the unit itself. The lug is not appropriate for transformers. Is there something else that can be used? So on the transformers, we always get it on the secondary side of the transformers. So at those those bolted connection points that would go into the bus duct and into the distribution equipment, that's where we would get it. It is not rated to be in any hot oil or anything like that. So the secondary lug connections off the transformers where we typically get that. Is there a way to have a low ambient temperature alarm in the HSM in a cold climate? Outdoor switchgears are provided with heaters to preclude condensation on internal parts. But so you can set the alarm at any location you want, and that ambient would take one point within the module itself, and that'd be the one that's calculating the ambient. So at that point, you would designate that at the lower alarm level, if you will. Hope that answers your question. Is there a relay changeover contact? Can we get, oh, here we go. Is the relay a changeover contact? Can we get signal green for good and red for problem? A relay changeover contact. Well, on this particular HSM unit, the relay, the internal relay contact will close upon any of those points in that unit reaching the first threshold. So there are no, the end user can choose to do red green. This particular unit would be mounted inside the instrument compartment, and therefore maybe even not be seen. So we want to address that with all the mapping that's coming from the HSM unit into a secondary system, or like your power management system. Can it be in a dry transformer winding? Have to look at that, Kevin, and see if that what that mechanically looks like. But at this point, I don't see why it couldn't. If there is a median point where fiber optics could be spliced and reconnected in the future to a main electronic unit. So the reason that that cannot happen, Hamid, is because the probe tip is expecting a certain time and wavelength, light wavelength from the HSM. So the splicing, you could certainly coil it and leave it, but splicing of fiber is not something that is allowed with this product. It is specifically calibrated from, the module to the tip. So we don't want any splicing going on, but certainly if you got a 15-meter fiber, you could certainly coil that and leave it for, the future installation of the fiber. Would this be suitable for use monitoring three-phase pumps in a wastewater wet well? My first inclination is to say no. The fiber is very robust, and it does work in many environments. I'm not sure the application fits, but I'm happy to talk further with you on that. And if you'll send me your contact information, I think Nick has your contact information. We can chat offline about that. Let's see what else we got here. Okay, I don't see any more. Anybody have any further questions? Again, if you want to address me directly, my email address is Shelly D, SHELLYD @gracetechnologies.com, and I'm happy to discuss any applications or any thoughts that you have about the product or your application.